Hello and welcome back to the video lectures on ordinary differential equations. So let us continue our discussion with the last method, which is Runge-Kutta method of fourth order. So this is the formula for RK method that we are going to use. As such, the formulas for second order Runge-Kutta method, third order Runge-Kutta method, and even higher order Runge-Kutta methods are available. But fourth order Runge-Kutta method is most frequently used method for solving ordinary differential equations. So this is the formula, and again we are going to work with the same setup of new value, old value plus step size times the slope. So on the left hand side we again have yi plus 1 is equals to new value of y is equals to old value yi plus the plus this term. So this term is new, and that term represents RK method. Okay, so that term was different for Euler's method and modified Euler's method, and you can evaluate the values of k1, k2, k3 and k4 using these formulas. Okay, so you have to simply substitute the values and find out the values of k1, k2, k3 and k4 and substitute those four values back into this formula to obtain the new value of y. Okay. Solve an example using RK method. So this is the given differential equation which we want to solve using RK method, and this is the initial condition given, and the meaning of this condition is that at x0 equals to 0, y0 is equals to 2. Using Runge-Kutta method, we want to compute the value of y at x equals to 0.2, at x equals to 0.4 and at x equals to 0.6, and it is quite obvious that we are incrementing the value of x by 0.2, and hence the step size in this problem is 0.2. Okay, so again this is the function. So let me erase this. Okay, so this term on the right hand side of this expression is the function f that we are going to evaluate at different values of xi and yi. For reference, again this is the formula for RK method. So let us begin with first iteration, and at the beginning of iteration 1 the values that we are going to require are x0, y0, f of xy and the step size h. So x0 is 0, y0 is 2, the function is x cubed plus y, which is the right hand side of this differential equation, and the step size is 0.2. So this is the expression, this is the resulting expression. If we substitute I equals to 0, so if we substitute I equals to 0 into the formula, then we get that expression. And to find the value of y1, we must first find the values of k1, k2, k3 and k4. So let us do that. So this is the formula for k1 from the previous slide. K1 is equals to step size times f of x0, y0, and here I evaluated this expression. I substituted the values of h 0.2 and the value of function is x cubed plus y evaluated at x0 is equals to 0, hence 0 cubed plus y0 is 2, hence plus 2. Okay, so the general form of the formula is x cubed plus y, which is also the right hand side of the differential equation given. So we are evaluating this at x0 comma y0. So x0 is 0 and y0 is 2, so that's why we have got that expression, and finally the value of k1 comes out to be 0.4. Okay, so let me clean it up. Okay. Then K2 similarly is the formula, and then substitute values here of x0, y0 and h, and K1 you can see that the value of K2 is dependent upon the K1. Okay. So we substitute the value of K1 here as 0.4, and then finally we evaluate the function at x0 is equals to 0.1 and y0 is equals to 2.2. Okay. So this 0.1 is, let me use another color. So 0.1 is the evaluation of this expression, and if you evaluate that expression we'll get 2.2. Finally we calculate the value of function, which is again x cube plus y at 0.1 and 2.2. Finally we'll get the value of K2 as 0.4402. Okay. So similarly, the value of K3 comes out to be 0.44422 and K4 comes out to be 0.490444. Okay, so you can just pause the video and do the calculations on your own. Finally, we substitute all the four values of K into the expression for Y1, which is this expression. And if we do that, we get the value of y1 as 2.443214, which is also the value of y at x equals to 0.2. Okay, so after iteration 1, we found out the value of y at x equals to 0.2. So let's move on to iteration 2, and this is again the formula for reference. At the beginning of iteration 2, we have the values that we obtained in the previous iteration of x1 and y1. So now we have incremented the value of x1 by 0.2, hence x1 is 0.2 for iteration 2, and we obtain the value of y1 at the end of iteration 1. The function remains as it is and the step size remains unchanged. Then we substitute the values into this formula. Again we calculate values of K1, K2, K3 and K4 similarly as we calculated during iteration 1. We substitute the values of K's into this expression of Y2, and also we substitute the value of Y1, so we get the value of Y2, or this is the value of Y. This is also the value of y at x equals to 0.4. Okay, so pause the video and do the calculation yourself, and make sure that you have understood the mechanics of calculations. Similarly, you can proceed to iteration 3, which will finally give you the value of y3, which is also the value of y at x equals to 0.6. Okay, so nothing much. This is everything about RK method, and we are actually done with the ordinary differential equation. Hume's method is very similar to this RK method. Okay, so I'm not going to cover it. I will soon upload the assignments related to all the topics that we have covered from Unit 4 and Unit 5, and these online assignments will count towards CA2, so make sure that you submit them before the deadlines.